Okay, Oscar, pay attention because you might forget. This is a real simple designing a galvanic cell from half reactions kind of question. I have included some simple directions on the right side just so you know the general layout, but you really don't have to, if you do this correctly, you really don't have to write all these small details out. You just have to look at one thing, which is going to be right here, the standard reduction potential. Um, Laser, yeah, this part right here, the standard reduction potential, to identify which of these two half reactions is the oxidation reaction, which would be our anode, and our reduction. And the way we check to see is which one has a greater reduction potential. And because we're looking to see which one's greater, obviously this one is more negative, smaller, and less so than zero. Um, this is a greater reduction potential, so this will be the reducing cathode. Here, we're going to look which one's greater. Obviously, equation 2 is greater. That is what's going to happen in our cathode. So we're going to write this whole equation here down in this first box, which is extremely annoying, but that's why I didn't want to write it out, so I could just skip to this step. Okay, so that's our cathode. Now our anode. Because these are written, I don't know if you could see here, these are written as reduction reactions as they were gaining electrons. You see, notice both of these are gaining electrons. Same thing here, they're both gaining electrons. So our now our difference, it's gonna be written in the opposite direction. Here I wrote down anodes oxidize, obviously, therefore you flip the oxidation reaction. So you flip this C2 plus aqueous plus electron equals Cu plus. You flip it the other way. So just to give you guys an illustration, this is what I mean. So you just flip the equation. It's the easiest way of explaining this. When you're writing the balance reaction, you're going to have to multiply the electrons so that they cancel out. Notice here in this over here on this side, I didn't have to multiply the electrons out because they were both 2. Um, you'll see that they cancel out, and I didn't have to worry about that because I didn't have to multiply the whole reactant side or a whole product side or the whole reaction, I should say, because that's more correct. Uh, Here, you're only going to have to multiply this side or this half reaction by 10 because you only have one electron. So to show you what that looks like, we're gonna here. This is gonna be long. All right, let's start off with just doing this. This might be easier. So because this is being multiplied by 10, this is going to be 10 Cu plus aqueous. Yeah. And then that's going to equal, we're going to get 10 electrons. Already multiply that, that's going to cancel out because we have 10 electrons on the reactant side. Now we write out 10. You could write it either or. Let's do it this way. 92 plus 6 waters. And then we're going to add our 10 Cu2 plus is aqueous. Do we have enough information? Yes, and the only difference now is that you subtract these two, the larger standard reduction potential from the smaller standard reduction potential. You'll see that here. If I'm not mistaken, let me see. Let's bust out our calculator. Have any batteries? Let me see something. Yeah, okay. So we're going to do 1.195 minus 0.15. Right? We're giving 3 significant digits, so we're doing 3 significant digits. And pray to God that that's right. Shit, I'm gonna have to make this smaller. Or this way because I couldn't see the check. Fuck you mean. Sorry. I guess we're doing more digits or less. This doesn't make sense to me. It's probably less, guys. Right? Because it wouldn't be 4. I guess it's more, but that's technically 3 significant digits. I don't know, guys. That's sometimes Alex's fault, but there you go.